Hey, how's it going, everybody? It's your pal Impossibum here with a Impossibum creation. This one is the magic square of squares. So if you're not familiar with what a magic square is, basically it's a square made up of several components. All the different lines and rows and diagonals sum up to the same number. So 2 plus 7 plus 6 equals 15. You can do that for all these rows. 4 plus 5 is 9 plus 6 is 15. You see every single different way you come at it. It equals 15. It doesn't have to be 15. It could be any number. That's just basically what the idea is behind the magic square. Now, the magic square of squares means that all of these have to contain squared numbers. So like 1 squared, 2 squared, 3 squared. So this would have to be like a 1 and a 4 and a 9. And then going all the way up, and then let me see, it would be 1 through 9, so the last one would be 81. You know, it'd just be all squares going all the way through it. And basically, nobody has ever found a magic square of squares. It's like some mythical, unfound, unrealized thing that people have been debating about whether it's even possible for it to exist for a long time. So what we are going to do today is write a program that, if it exists, will be able to find a magic square of squares. Now, mind you, this is going to be a Python program. And if it exists, it would literally have to run for like 1,000 years or something crazy. So will we actually find it? No, unfortunately not. But we will write a program that can find it, is capable of finding it, and I'll walk you through the logic of how this is all going to work. So, ta-da! It is already written. I know it's a magical. I got bored today and decided to do this, and I was like, you know what, let's make a video about it. So here's our magic square class. This is going to be how we construct this magic square, and we check its contents to see if it's actually, you know, the true magic square of squares, that, you know, the square of legends. And more often than not, by a large margin, it is not going to be so. So let's look over the initiation function here. Init function. It takes in basically just one argument, which is this contents, and that's just the numbers that you're going to put in. This is just one single list. It could be a list of lists, so you could treat it like Cartesian coordinates and whatnot. I just decided to go with a single list. You know, however people want to do that is up to them. Size is basically just the length of the contents squared. Square rooted. That'll give you, you know, how many wide it is and how long it is. So that you can, you know, reference that for things later on. See, we have the repr and string functions. Basically, if you print string or print this object, what is it going to say? This will be what it says, essentially. All right, so now basically we're going to have to go through our contents and say, is it solved? Well, how do we know it's solved? Well, like I said before, we have to make sure all the rows, columns, and diagonals equal the same number. What number it is, it doesn't matter. But they all have to be the same. So if one line summed up equals 15, every other single row, column, and diagonal has to equal 15. So what do we do here? We take this line value, say, okay, this is the top line, going from top left to top right. Every single thing we find had better equal this same value, or it's not officially solved. You know, it's an improper square. So this is what we're going to do. Basically, this is the line this is what it has to equal. And we're going to check every single horizontal, every single vertical, every single diagonal. Say, hey, do you equal this? If not, return false. This is a bad square. It doesn't work. So let's check over these checks real quick. You see right here, the first one we check is check horizontals. So basically, that's what we're going to be doing. We're going to iterate through the top line to say, hey, does this thing equal target right here? This is the target. This is the value we fed in right here, saying, hey, this is the value that everything has to equal. All right. So for I and range self.size, remember we set self.size up here. This is how many rows we're going to have to iterate through here. And we say, all right. So in this case, particular case, it'll be 3 for all my testing down here. But as you can see here, I've tested it with larger squares. It does work. You can have as big of a square as you want, but then the problem just becomes exponentially larger. And if you thought, you know, finding a magic square of squares for 3, 3 by 3 square would take a long time, just imagine a 4 by 4 or 5 by 5. That would be absolutely ridiculous, beyond the regular ridiculousness. All right, so let's check it out real quick. First, we're running a sum. Basically, we're splitting up the, we're slicing the self.contents. And basically, all right, we're saying, we're starting off at I times self.size. Starting off, this will just be 0. So from 0 to I times self-size, which would be 0 again, plus self-size, which would be 3 in this case. So this is from index 0 to 3. And we're going to sum up every single value in there. So this is from values index 1, 0, 1, and 2, in this case, by a 3 by 3. And we say, okay, does that equal target? If not, we're returning false. We're not even going to continue going through the rest of this. And then we iterate to the next one. Okay, does the second row equal that? Does the third row equal that? And if it goes through this and they all equal it, well, then we go ahead and return to true. It is that simple. That is how that works. I will have this code up on GitHub if you guys are interested, by the way. So if you're not quite, if you need more time with it to figure out what's going on, you just want to reference it later, whatever, it'll be up on GitHub. I'll have it down in the description for you guys. This time we are checking the verticals. So here you can see we're creating a new list again, going over all the indexes. And we're saying, okay, starting from I, which in this case is going to be 0, and we're going to skip forward every self.size, which is 3. So we're going to start at 0, and then we're going to get 3, and then we're going to get 6, and that's going to be our 3 things. And we're going to say, okay, at index 0, 3, and 6, let's sum them up. And if they don't equal the target, well, we're going to have to return false because, that's part of the whole completing the square thing. And then we go on to the next one, which is going to be starting at 1, and then it's going to be 4, and then it's going to be 7. And then we say, okay, do those indexes, equal up to target here? And if they don't, we're going to return false. And we do that for every single vertical line. And then we have diagonals. This one here, we're just going to go over the diagonals. I'm not going to step through this one because I'll probably give myself a headache doing it, to be honest. It works. I can prove to you that it works at the bottom. We'll step through it real quick. This one right here checks if it's going from top left to bottom right. This one right here checks if it's going from bottom left to top right. And let's run a couple checks real quick. I have a couple of squares here. Like this one here is just 1 through 9. We know this one will not work. This one is all 9s, which our program will say works. But whenever you're doing a magic square, they have to be different numbers, essentially. This one right here is a legit working one. This one, again, is a longer one, a 4 by 4, but one just, 1 through 16, so it's not going to be an official magic square. And this is a 4 by 4 magic square that actually works. So let's go ahead and run this real quick and verify that these actually work real quick. So run magic square. We'll bring this up here. So you can see this one. It says, nope. Let me go over what we're printing out exactly here. I'm basically just printing out the square and then printing out its solved method to indicate whether the algorithm thinks it is solved or not. So as you can see with this one right here, it says, nope, it's not solved. This one, 99999, it technically solves because all the rows, columns, and diagonals equal the same number, but they're not different numbers. And I don't have that check, and I could, but I don't. Stuff happens. We got another one here. This one is a legitimate magic square, and it says true. This one is 1 through 16, so just another test square. And this one verifies, nope, that's not a proper square. And this one is a magic square 4 by 4, and this one is a proper magic square. And it verifies is true. So we have a working magic square algorithm here for verifying whether the square is truly magical or not. So now that we have this, we can create some kind of mechanism for generating magic squares for us to then verify whether they're officially a square of magic squares or not. So let's go over to our square of squares solver, which is right over here. Let's go over the tools real quick. We're going to be using iter tools. Basically, permutations is a function within iter tools, which basically, if you feed it a list, it'll give you every single permutation of that list, which is a lot. Honestly, it's factorial. So if you have a list of 9 objects and you want to feed, all the different combinations back, it's going to be something stupid like 380,000 different combinations. Factorials get huge really, really fast. Anyway, so let's see here. We have a squared list. We have a basic function here that just gives us a version of the same list, but with all the contents squared. Because remember, we're looking for a magic square of squared numbers. So instead of, generating squared numbers, I'm just going to generate normal numbers and just square them. Basically, we're just going to go iterate, 1 through 9, then 1 through 10, then 1 through 11, so on and so forth. All right, so now we're going to generate and evaluate. This is our function that's actually going to generate squares and check and say, okay, are you a magic square? Are you not a magic square? Let's look through it real quick. We're in a while true loop, which means this will just keep going for all eternity. The only way it's going to break out is if the square is solved and we return. and that'll magically break us out of the while true here. Of course, we're just gonna, break out of it at some point, just, with a keyboard interrupt when we actually run it. But, for as far as things goes, this will never actually stop by itself unless it returns a square. Right off the bat, we're creating a contents here. Basically, we're saying, okay, this is the number list we have to work with. All right, we set our max int right here. Size times size. Let me see, I actually call it down here. Squares, generate and evaluate 3. So we're making a 3 by 3 square grid, essentially. When I'm calling this, that is exactly what that's doing. If you're not sure what this is how you can import functions from other things and not actually run all their logic. That's why you use things like this. Just throwing that out there. Just a little tidbit here and there. Let me see here. Okay, so this is creating our list of all the different numbers we're going to be using in this iteration. This is our permutations, where I talked to you about itertools permutations. This returns a generator object. So basically, I feed in, this is our contents list that we make right here. I'm saying what size of the list I want back out of it. And I want the same size as what I'm putting in. And so it's going to be feeding me back all possible permutations of that list at a length of 9, because we're making a 3 by 3 grid. And now we're just going to feed through it. Basically, we're going to iterate through this mutations generator object with a for loop. And we're going to say, okay, give me, my new iterated permutation. And first off, I'm checking, because every single time you iterate up to where your max integer here is larger, you don't want to do all the same calculations over again. So any contents here that is generated that does not contain your max integer is something you have calculated previously, so you don't need to check it again. So the first time it doesn't matter, really, but it doesn't hurt anything, because it's the max squared is going to be in there anyway. But later on, as you keep going on, when you get up to, your max number is 10 and your max number is 11, well, if your new contents that are being generated here doesn't have that number in it, it's going to be something you've already calculated. This is just to nip that in the bud, so we don't have to calculate the same thing over and over and over again. And I'll show you a demonstration later on, what happens with that, how much time we actually save. Over a long period of time, it'd be quite significant. Over just doing 1 or 2 iterations, it's actually not overly significant. Here we're just counting up. We're iterating our square count. So saying, hey, how many squares have we actually made? We're creating our square here with the contents. So this is what we're happening for every permutation. We're feeding that permutation into the magic square. And then we're running our square, square.solve thing. This is this one right here, where we check to say, okay, does everything add up to what we think it should add up to, which we have defined right here. And it's saying, okay, does it add up? Well, let's return that square. We found it. Everything is honky-dory and magical. If not, it just goes on to the next one on the list. That is all there is to it. When you get out of all these permutations, like I said, there will be a lot of them. Then you just go on. We're doing a little printout here saying, okay, this is how many things we've tested so far. This is how many squares we generated. And then we're moving the max integer up. We're moving the max squared number up. And we're moving on, creating a new permutation object and iterating through all of them all over again. Now let's, this has been a whole lot of talking. Let's just see it in action. Let's just see it happen. So let's go ahead. I'm going to go ahead and hit Run Squares Solver. And you see exercise and futility initiated. First off, this is a Python program. If you really wanted to do this seriously, you would not do it in Python. It is a scripting language, which is great for prototyping and just doing silly projects. But the problem is, it is not very performant. So if you really, really, really wanted to find a magic square of squares, you wouldn't really use Python. So let's go over here real quick. We see the first one here. These are all the different contents that we got the first time around. These are the squares. And there was 362,000 different magic squares generated. Can you believe that? That's so many magic squares we generated in just like a second on this one. All right, so nothing was found there. So we increased our size to hold the 10 by 10. So 10 times 10 was 100. So that's the next square in the list. And then we did 11 times 11, which is the next square in the list. And we still haven't found anything. Can you believe it? What happens when we do 12 by 12? Will we find it then? Let's find out. Ah, darn it. We waited another couple minutes, and we didn't get it with the 12 by 12 square, which is 144 here. So, like I said, this is something that would likely go on forever. But this is a solution that would technically work. You let it run long enough, and if it exists, it will eventually find it, assuming you don't run out of memory and the world doesn't end and your computer still works for 1,000 years and so on and so forth. Anyway, I thought this would be a fun, silly little project to share with you guys to get you to know what kind of silly little projects I do. I also do a lot of other coding stuff. If you guys know me at all, or you know Cameo, I'm Cameo's developer. She's a bot for Rocket League, which is one of the best in the world. She's currently the 1v1 champion. I also do all sorts of other things. I'm currently working on a chess bot, which I'm going to be making a video for. So if you're into silly coding curiosities, why don't you go ahead and hit that subscribe button, click that bell icon so you know when I put out new content, smash that like button, leave a comment down below. Thank you guys so much for watching. If you have any ideas for future videos, let me know. It might just happen. Thank you guys so much for watching. I'll see you next time. Bye-bye.